This video is all about integrating with inverse trigonometric functions. We've already done quite a lot of work differentiating them. We've shown previously that arc sine can be differentiated to be 1 over the square root of 1 minus x squared and so on. But we know that whenever we learn something about differentiation, we also learn something about integration. Because we know that the reverse process, if I integrate 1 over the square root of 1 minus x squared, it's going to give me arc sine. If I integrate minus 1 over the square root of 1 minus x squared, it's going to give me arc cos. If I integrate 1 over 1 plus x squared, it's going to give me arc tan. So we actually know some integration results of some quite awkward functions. Let's prove one of them though. Let's prove the third one. Let's prove that when you integrate 1 over 1 plus x squared, you do get arc tan. Now I'm going to do this with substitution. And the substitution I'm going to use for this is that x equals tan u. And the reason why I picked tan u as my substitution here is because when I substitute this in on the denominator, it's going to give me 1 plus tan squared. Which is good because 1 plus tan squared will simplify to be sec squared. And then hopefully there'll be some simplification. So as always with integration by substitution, the key thing is to differentiate your substitution. So I'm going to differentiate both sides with respect to u. Differentiating tan u gives me sec squared u. So my dx is going to be replaced with the sec squared u du. Right, let's substitute these things into my integral then. I've got 1 over 1 plus x squared, so that's going to become 1 plus tan squared u, multiplied by dx, which is sec squared u du. And like I said before, the denominator there, 1 over the 1 plus tan squared becomes sec squared u. And hopefully now you'll see that the sec squareds are going to cancel out. And it's just going to be the integral of 1 with respect to u, which is just going to be u plus c. I now need to swap u back. Now I come back to my substitution and I remember that x is equal to tan u, which means that u would be equal to arc tan x. So putting that into my result here then, I got arc tan x plus c. So that's how we can use integration by substitution to prove these results. What about more complicated results though? What about this one? Now, we've already seen that we just saw a moment ago that this integral gave me arc tan. Let's see. Now notice the only difference here is we've got an a squared, we've got a constant on the bottom. The only difference is this rather than this. So what I'm thinking here is, can I rewrite this? So actually, this isn't an a squared here, this is a 1. And I can. What I'm going to do is I'm going to divide my denominator by a squared. Obviously, if I do that, I would have to divide the numerator by a squared as well. But that's fine, we can deal with that. So I've got my 1 over a squared on my numerator, which actually is just a constant, so I'm going to take that outside of the integral, like that. And the key thing now is that a squared divided by a squared is 1. And then I've got the plus x over a all squared. Now, remember the result. I could go through the whole process we saw a few moments ago. But remember the result that, let me put in a different colour. The integral of 1 over 1 plus x squared is arctan x. So I'm going to use that with this result here. The only difference is I've got this x over a instead, which is fine because I can just use the reverse chain rule to integrate that, because that's just a number, it's just a constant. So let's do that. So I've got the 1 over a squared at the front. Integrating this function will give me arctan x over a. And then by the reverse chain rule, I need to divide by 1 over a, which is the same thing as timesing by a. Hence, we have a 1 over a coefficient. Point is, by dividing through by the a squared there, I've got this new formula, a more general formula, and you have these in your formula booklet. We could do a similar thing with the arc sine as well. So we know that if we need to integrate 1 over the square root of some number minus x squared, we can use arc sine. If there's no square root on the denominator and it's just a squared plus x squared, or rather just a number plus x squared, it doesn't have to be a square number there. We'll talk about that in a minute. But we can use arctan to integrate that. So the rest of this video is now looking at examples of these new results. So here's the first one. I want to find the integral of 4 over 5 plus x squared. So first thing I'm going to do, I'm going to take that 4 outside. So I've got a 1 on the top. I'm now comparing this, or rather this, to my results at the top here. There's no square root involved in my one, so it is definitely not the arc sine. It's going to be the arctan one. So comparing my results to the arctan, my a squared is 5. Which means that a would be root 5. Other than that, I can just use the result directly as it is. So I've got the 4 at the front. Now, using the result directly as it is, I've got the 1 over a, so 1 over root 5, arctan of x over root 5, plus c. And other than simplifying the coefficients at the front here, the 4 times 1 over 5 is 4 over root 5. That's it, we're done. We've integrated it using these results. So the only tricky thing here is determining whether you're going to use the arcsine one or the arctan result, and then just figuring out what the a value is going to be. 2 more examples. Right, first one here, we've got the integral of 1 over 25 plus 9x squared. Now, again, notice there's no square root with this one, so I'm hoping it's going to be the arctan result that I'm going to use. Do notice, however, that I've got a 9x squared here, and I don't want a 9x squared. I just want x squared. So I wanted to be able to divide by 9 here. to get rid of that, which I can do. I can take the 1/9 outside here, like I did before. And this will now be 25 over 9 plus x squared. Now I can use the result from above, where a squared is going to be equal to 25 over 9. So a is 5 over 3. So using the result from before, we've got the 1 over 9 from the front. Right, the 1 over a. So 1 over a is going to be the same thing as 3/5. Arctan of x divided by a, so x divided by 5 over 3, which is going to be 3/5 x. And again, other than just simplifying the coefficients at the front here to be 1 over 15, we're done. Next example, we want the integral from minus root 3 over 4 to plus root 3 over 4 of 1 over the square root of 3 minus 4x squared. Now, we've got the square root here. So that's making me look at the first formula, the arc sine one now. Again, I don't want that to be a 4x squared. I want this just to be a single x squared. So I'm going to have to factor out a 4. But I do need to be careful because that 4 is inside the square root. So let's be really careful with this. I can't just take a 4 outside there. That's wrong. The 4 has to be square rooted. So it won't be 1/4 I'm factoring out. It'll be 1/2. Then on the inside of the square root, I've got the 3 over 4 minus the x squared. This now matches the form of the arc sine in the standard results, where a squared equals 3 over 4. So a would be root 3 over 2. Excuse me. So using that result, then I've got the half at the front there. It's going to differentiate to be arc sine x over a, so x divided by root 3 over 2 will be 2x over root 3. And then you can substitute your limits into this and then divide it by 2, and if you work that through, you should get pi over 6 as your answer. Okay, last example. Right, now when we look at this, we've got the integral of x plus 4 over the square root of 1 minus 4x. Now to begin with, I don't like at all the x plus 4 on the top. That's like neither of these results. Both of the results we've seen previously have a 1 on the top. But it's okay, because I can split this up. I'm going to think of this as being the integral of x over 1 minus 4x squared plus the integral of 4 over the square root of 1 minus 4x squared. So I'm just splitting it up to be the x over the square root of 1 minus 4x squared, and then the 4. I can work those out separately and then add the results together. Now, the first term here. Now, first term here, we don't actually need to work this out we don't actually need the standard results. We could have done this in regular A-level maths, because we can use spotting the derivative for this. I can think of this as being x times 1 minus 4x squared to the power of minus a half. When I look at the inside here, the derivative of that is minus 8x, which is good. I can get a minus 8x as long as I have a minus 1/8 at the front of that integral. That will allow me to ignore the derivative completely. Raise the power by 1, so the minus a half becomes plus 1/2. Divide by the new power, so dividing by 1/2 is the same thing as timesing by 2. And there we go. So that first term integrates just to be minus 1/4, 1 minus 4x squared to the power of a half. Right, let's have a look at the second term here. Now, we certainly can't use spotting a derivative here, because there's only a 4 on the top, not the x. But we can now do this with our standard results. If I factor the 4 outside, that's going to give me a 1 that I want. So that's nice, I like that. So let's do that as my first step. I'm going to think of this as 4 lots of 1 over the square root of 1 minus 4x squared. So that's one step closer to being able to use the standard results. But remember that I can't have the 4 in front of the x squared. I can't have that. I need to factor that 4 outside, which I can do as long as I square root it, because it is part of the square root. So I've got the 4 on the numerator there. When I factorised out the 4 from the denominator and square rooted it, it will give me a 2. So we have that. Then I can use my standard results now. Well, first of all, actually, let me do the 4 divided by 2. The 4 divided by 2 at the front is 2. I'm going to use my standard results where a squared is equal to 1/4, so therefore a is equal to 1/2. And so I'll get 2 lots of arc sine of x divided by a half, which is 2x. And there we go. We have integrated that whole function. So let me just summarise that example, because that is quite tricky. I took the function and split it up to be x over the square root of 1 minus 4x squared plus 4 over the square root of 1 minus 4x squared. I then did those integrals separately. This one, because it had an x on the numerator, I noticed that could be made to be the derivative of the 4x squared. So I used our traditional techniques of spotting the derivative from regular A-level maths to do that one. The second one, I couldn't use that technique because I only had a 4 on the top, not the 4x. So I took the 4 outside. I then wanted to deal with that 4 on the inside there, because remember it has to be a 1x squared to use the standard result. So I took that 4, I factored it outside of the square root. When it comes out of the square root there, when I square root that 4, it would become a 2. And then when I take that 2 outside, that 4 over 2 became the 2. The 1 here, when I divided that by 4, I got the quarter. That's my a squared value. So my a value was 1/2. So now using the standard result, where I have arc sine of x divided by a, so x divided by 1/2 is 2x.